Problem number 69 in your textbook is one of your assigned problems. And this is when we get a complex ion situation meeting a KSP situation. And I would actually say this is less complex than just looking at complex ions by itself. You can see how this would work. So this is something that would be more realistic to the type of question you could see. And again, understanding it qualitatively, a little bit quantitatively, trying to pick up what's happening in this. So let's look at this question. And the first question is really just looks like a type 2 problem where it says calculate molar solubility of AgI in pure water. And it gives you the KSP. So if I look at it, AgI breaks into Ag plus and I minus. So it's going to be equal quantities of Ag plus and I minus. You can call each one X. You can say KSP equals X times X or X squared. So X equals the square root of KSP, which is 1.2 times 10 to the negative eighth would be X. And that would be the solubility right there in distilled water. Okay, let's think back when we did common ion effect. If we add Ag plus, it's going to shift equilibrium left, and it's going to make the equilibrium even less soluble. But in this case, we're going to be doing this in NH3, which has the opposite effect. It removes NH3, so by it removes Ag plus, so by removing Ag plus, it should become more soluble. So in a way, it's kind of like the common ion effect, except it's the opposite. You're removing a common ion, and then it's going to drive the solubility, drive it to dissolve more, at least make it more soluble than it was before. So let's take a look at how that works in this situation. We have, let's see, so the formation of AgNH32 is 1.7 times 10 to the 7th. And we know what the AgI thing is. Let's take a look in the KSP for that. Let's meld these two things together. And what we'll do is we'll look at this and say AgI forms Ag plus I minus, that's the KSP of 1.5 times 10 to the negative 16th. And then we're going to say Ag plus 2NH3. Notice I'm doing the combined form to get the whole ligand, AgNH32 plus 1. And that's the Kf for the formation of this would be 1.7 times 10 to the 7th. So what I'm going to do is add these two things, and it looks like quote unquote the intermediate when we do this would be the Ag plus that drops out. So we end up with AgI plus 2NH3 forms AgNH32 and I minus. Okay, and because I'm adding these two things, the KSP and the KF, I multiply these things there. So notice this is really, really small, but when it gets multiplied by 10 to the 7, it's small, but not as small as it was before. So now we're at 10 to the negative 9th right here. Okay, let's look at some of our numbers. We're given 3 molar NH3. Whoops, kind of lost that. But in the problem we were given 3 molar NH3. So let's take a look at that. And let's see what other things we have. That's pretty much the only thing we need to pick out from there. We don't have anything before it breaks up. So this is going to break up into this and this. But before it breaks up, and how much is it going to break up into? It looks like the ratios are going to be the same, X and X. Okay. When it does break up, it's going to use some of this. So technically, this is going to be 3.0 minus 2x, but this 2x is going to be small compared to the 3.0. So now we can solve this. We know the K value. Okay, we can say AgNH32 here. We can say I minus here. We can say NH3 squared here, which matches the KSP expression for this. Notice the AgI drops out of this equation. And then it just becomes X squared over 3 squared. And ultimately, I can solve for X squared. And I know the 3 squared is 9. I know this is the K value from up here, the 2.6 times 10 to the negative 9th. And I get 2.3 times 10 to the negative 8th. Sorry, that's sloppy. I take the square root of that. I get 1.5 times 10 to the negative 4th. Still not that soluble, but let's do a comparison. 1.5 times 10 to the negative 4th compared to 1.2 times 10 to the negative 8th in water. And that's 4 orders of magnitude. I mean, that is almost 10,000 times more soluble than it was in water. So there's a significant contribution to making it become more soluble. Okay, let's go to our last question here. Compare the calculated solubilities from A and B. Explain any differences. I think we did that. And again, think about it in terms of the common ion effect. What's happening is we're not adding Ag plus and driving equilibrium to the left, we're removing Ag plus, which drives equilibrium to the right. Or instead of saying drives it to the right, allows us to consume reactants to form products and makes it more soluble. So looking at the language, we said adding NH3 increases the solubility of AgI, added NH3 moves Ag plus, and causing this to shift to the right. And I know that's shifty language, okay? So we will say it causes reactants to be consumed to form products, okay? And then making it dissolve better, the AgI dissolve better. All right, hope that helps. There's a question number 71, which is very much like that. You can use this as a model to solve that one. Thanks.